So welcome everyone to our third Journal of Mechanical Design webinar. And this webinar is focused on design for additive manufacturing. My name is Fiona Zhao. I'm an associate professor at McGill University in Montreal, Canada. I co-organized this session with Julián Norato from University of Connecticut. Julián, would you like to say a few words to the audience?
Hello, everyone. I'm really glad that you're joining us today. And we have a terrific panel of speakers lined up for you. And I look forward to the discussion today.
Thank you. And also the JMD webinar series have been initiated and organized by Fayez and Ahmed in MIT. Thank you, Fayez, for organizing this terrific venue for us to meet and exchange ideas. And today we have 4 outstanding speakers who's leading in various topics in design for additive manufacturing domain. We have Saigopal Nelaturi from Park. We have Carolyn Seepersad, and Kade Whitefoot, and Nicholas Meisel. We will have individual introduction to each speaker later on. First, I would like to discuss a few housekeeping notes. So in our plan, each presentation is 10 minutes, followed with 5 minutes of question specifically for this presentation. So if you want to ask question, I would ask you to either type in the chat or you raise your hand. Julián and I will cue your name when we for you to ask question directly. And we're hoping to keep the time of speaking, presentation, and question for each individual presentation to 1 hour. And we will jumpstart our panel discussion at around 1:10. The panel discussion is about 20 minutes long. We will start with a few questions Julián and I have. And then throughout the discussion, all the audience are encouraged to ask questions. Again, use the same manner, which is type in the chat or raise your hand. We will try to reach to everyone who raised the hand. But I understand today we have large number of registration. We'll try to accommodate as much as we can. Now, apart from this, we also have another venue, Gather Town. In the chat, I believe there will be a link also provided here, apart from your email from the registration. The Gather Town would start at 1:30. So I tried it for the first time on Monday, and I realized it's a rather interesting experience. So when you open that link, make sure you have to click on some buttons to have your little figure navigating, reach to certain locations. Then it will lead you to the meeting rooms. So this is the meeting room. The little figure here is Fayez. So you can use the arrow buttons on your keyboard to move your little figure whenever you are close to other people. You can start to chat with them. You can see them on the screen, and you can start to talk to them. So this is a general idea of using Gather Town. It's a virtual way of meeting people, talking people as if we are physically in a room. So that's all the information from me, I believe. And then Julián, I think we are ready to start the presentation. Would you please introduce the first speaker? Thank you.
Yes, it is my pleasure to introduce Dr. Saigopal Nelaturi. He obtained his PhD in mechanical engineering from the University of Wisconsin-Madison in 2012. And he's currently a research director at the Palo Alto Research Center, Park. And he's going to talk to us about a paper that he and his collaborators published in 2020 at JMD. Sai, the floor is yours.
Thank you, Julián. Thank you, Fiona, for the introductions. It's my pleasure to be here today. And as Julián was saying, I'm going to be presenting a paper that is titled Manufacturability-Oriented Model Correction and Build Orientation Optimization for Additive Manufacturing. And I'm presenting this paper on behalf of my co-authors, and this research was funded by DARPA. And As Julián said, currently I am serving as the research director for all our research in 3D technologies at Park. That includes design, manufacturing, and materials research. So going to this paper, the motivation really for this paper comes from the gap that exists between the ability for design for additive manufacturing to exploit what we can do with the manufacturing process to fabricate really complex geometries, and the work that needs to be done in order to process three-dimensional models in order to make them manufacturable. Some of the processing work that needs to be done is really in terms of the representation of the geometry itself, because of issues such as manifoldness or non-manifoldness and water tightness or the lack thereof for meshes that need to be processed in order to make them printable. And there's a lot of work done in that space. And in fact, there's several commercial off-the-shelf software to do that. But then there is also the issue of designing the part in such a way that it is compatible with the capabilities of the printer that is going to make it. So often there are challenges either because of the printable resolution or the feature sizes that you have. There needs to be fixes that have to be done on the design model in order to make it printable. And there are several advantages to doing that, or there are several reasons to do that, because you want to be able to accurately approximate the as-built shape of the part. That gives you a good understanding of how the part is expected to perform in practice, as well as it gives you an accurate approximation of the cost. And fixing the model to make it printable also identifies regions where you need to do machining, post-processing, and identify how much work needs to be done to make the part completely processed and fabricated. And so the other motivation is that when you do this kind of fixing, it often happens at the slice level, because the way you slice the part in order to build it and print it is going to affect the kind of changes that you need to make to the geometry to make it printable. So there is a coupling between the analysis that you do for printability, as well as identifying the optimal orientation to make the part. So looking at what it takes to fix 3D models to make it printable, looking at it from a geometric point of view, mathematical morphology provides the framework, mathematical framework required to analyze printability based on a concept of sizing. So essentially what that means is you are, for a given slice, or you can even do this in 3D, there is a feature called a structuring element, which is basically what you assume to be the smallest printable feature, or a feature size for a geometric quantity of interest, such as a thin wall. And the size of this structuring element is going to identify the regions that are printable in the slice or in the 3D geometry as a function of how the structuring element can fit inside the geometry. So the morphological opening is a mathematical operator that actually does this very formally and precisely. And it is a combination or composition of two operations. The first operation is called an erosion, where essentially you're identifying all the translations of the structuring element, which for practical purposes can be considered to be a disk, where it completely fits inside the slice. And one of the properties of the erosion, which is actually used quite a lot in image processing, is that it kills small features. As you can see on the figure on the right, you have this dumbbell-like shape made of two squares and a connecting rectangle. And when you do the erosion, what happens is that it identifies all the regions where the ball can fit inside the square. And because the disk is slightly larger than the connecting section of the two squares, it actually kills that feature entirely, because none of the locations inside that connecting segment are places where the disk can fit. And it reduces the size of the square. So you can see there's a topological change from the initial slice to the eroded slice. And then when you construct a dilation of that erosion, which is essentially a sweep of the disk by all of these translations, you get a resulting structure that corresponds to what is printable. In the case of a simple shape like a square, the morphological opening corresponds to rounding off the sharp corners that you have in a 3D printed slice. But because the erosion changes the topology of the slice, you want to look for other techniques to be able to capture small features. One of the standard approaches used in computational geometry is to use this idea and properties of the medial axis or the medial axis transform. And when you use the medial axis, it can be computed for polygonal shapes in terms of the Voronoi diagram. And when you compute that, there's a lot of extra work that needs to be done to extract the relevant features. So essentially, what we've done is to come up with a technique in order to construct a shape that looks like the medial axis, which is very, but without all the added overhead and complexity of post-processing, directly from a representation of the input slice. So this is a figure from the paper where you can see going from left to right, if you have a three-dimensional shape, first what we do is we, depending on the build orientation, we slice the geometry and we construct binary images of the slice geometry. And then what we do is we construct a thinning process, an iterative thinning algorithm, which corresponds and converges to a shape called the mesoskeleton. What the mesoskeleton does is it identifies shapes that are smaller than the printed feature size, but retains the topology of the slice, without losing features that you have in the erosion or other morphological operations, such that when you construct the dilation or the sweep of this slice by the structuring element, you get back an accurate representation of the corrected slice. And when you stack all of these corrected slices together, you get a voxelization of the as-built part. Okay, so the the interesting properties of this mesoskeleton can be seen from this example slice here. So the example has been constructed to show some very fine features. And if you did a classical erosion or a medial axis transform, the amount of work that you need to do to classify those thin bars that are connecting the features of the shape are going to be substantial. And so but however, with the mesoskeleton approach, the algorithm thins images up to the erosion without actually going so far as to changing the topology. And the skeletal paths are created for the very fine features, as you can see here. And so this is topologically consistent. The precise definition of it is that it is homotopically equivalent to the initial shape that you start with. And you can come up with accurate representation of the as-built geometry. So what we've done is to actually print parts, and of course, you can look at the paper for all the details of the algorithm. But to get a high-level understanding of it, we've actually printed parts, and when you start from a nominal representation of the shape on the left, and you print it without any of the corrections that we're making, it can lead to a lot of failures in the printing. So a pathological case is seen in the second row where you have a hollow sphere, and because the walls of the sphere are thinner than the printable size, you get basically just junk, when you print it. And so when you apply the model correction with the appropriate amount of feature thickening, then you get a spherical shell as expected. So these types of feature corrections become quite important. And they're also coupled, as I said earlier, to the build orientation. So one of the other things that we've explored is to figure out how to identify the orientation that minimizes the amount of fixing that you need to do for the designed part, and find out how to minimize the absolute difference between the corrected and input slices. Now, as you can see, there are changes that happen in this process of constructing the mesoskeleton. We can round off corners and remove material, or you can add material at a strategic location. So you want to minimize the absolute difference between the corrected and input slices. You can weight the optimizer to either have the correction be equal in terms of the added and removal features, or you can bias it one way or the other. Then the design variables we use are the orientation angles, and we use a derivative-free simulated annealing approach. It can be time-consuming, of course, but the algorithm shows that we can optimize the orientation to minimize any kind of fixing. So that was a brief summary of the paper itself. And I would like to maybe close by adding a few remarks about where this research is going and how we're continuing it at Park. So there is work we're doing how to integrate this kind of work with post-processing, because no additive process is truly standalone. There's going to be some machining involved at the end of it if you want to get mating features and tolerance features and things like that. So the accessibility of the additional material by post-processing subtractive tools is going to be important, especially when you consider the geometry of the subtractive tool, as well as multiple degrees of freedom. Then computations, we've also extended it to get to very high resolutions, like at manufacturing resolution. For example, at that direct metal laser sintering resolution, we were able to voxelize the geometry of that feature and interactively render and represent it. Then there are inverse problems that we would like to solve, or we should probably should look at closely as a community, where it includes the interaction between additive and subtractive process planning, and then turning it around to design parts so that you know of the sequence of additive and subtractive processes that are needed to process it. And ultimately, we're taking it one step further and integrating this with physics analysis, where we're simulating the multiphysics of the process, and identifying other deviations from the nominal geometry, such as the existence of porosity in printed parts, so how close we are to the dimensional accuracy we desire, and surface roughness and other such properties. And with that, I will close my presentation. I hope.
Thank you very much, Sai.
Yeah.
No, you're perfectly on time, actually. So we open now the floor for questions. So as a reminder, either please type your questions in the chat and we'll relay them to Sai. Or if you prefer, you can raise your hand, and when we give you the turn, then you can unmute your mic and ask directly the question to Sai. Okay, so there are no questions yet. So in the meantime, I will ask one. So it seems that from the design perspective, you could avoid some of these challenges by making sure that you don't have features that are smaller than the print size to start with, right? So I mean, do you think that would be essentially a cure to these, or not necessarily?
Well, the print size is one of the challenges we have to deal with. Of course, you can design parts to be for all the features to be above the print size, but then there are other issues such as the wall thickness, and then there are multiple scales at which you want to be able to design features. Furthermore, when you start looking at realistic representations of the melt pool, for example, right, like then the shape is going to be non-trivial. And so when these operations hold for those kinds of non-convex representations of the structuring element as well. So when you combine the representation of the melt pool geometry with the kind of feature sizes that you like at different scales, then just designing for a threshold feature size only goes part of the way, right? And so I think we need analysis like this up front. But your question is valid in the sense that if you know what those thresholds are and how to include that as a part of the design optimization process, I think that's still a question that needs to be investigated further.
Thank you, Sai. I'd like to follow up question, and after that we have a question typed in the chat. So if you can go back to the last slide where you were discussing the future. Yeah, for example, in a figure, you would have, so the system in the end is able to at least identify or modify the geometry based on whether it's manufacturable or not. And then when we do such modification, how do we consider functionality or performances requirement? Because if you change it, right, obviously the end performance would change, like stiffness or strength or however you name it.
Yeah, good question. So the goal is to try to minimize any kind of change you do to the geometry, right? So you want to retain the design geometry as much as possible. So I think of it as basically a material addition process that can be undone. So if you add some extra material because of additive manufacturing, making sure the walls are thick and things like that, you also want to make sure that the way you're adding the material is done in such a way that you can eventually take it out later with the machining tool, right? Like, and that raises a lot of challenges. Like this geometry that is shown here on the top is a pretty complex shape. And depending on, so if you look at the region where the plane shows the slicing, the figure at the bottom shows the resulting slice, and all of those little tiny features marked in green are below the printing resolution. And if you try to add material there, you can do so and make the part printable, but the tool is has such a shape and degrees of freedom that it simply cannot access those geometries. So you have changed the geometry and you've changed the functionality. So that is not, so I would say that the part is not manufacturable as a composition of additive and subtractive manufacturing. So you're right, but without having a mechanism to undo these changes, you might be changing the performance and the functional characteristics of the part, which is part of the planning problem here.
Thank you.
So I will relate a question in the chat is from Blasea, and the question is, what flexibility is there to adopt across multiple AM technologies to account for material process design?
Could you repeat that, please, Julián? I kind of lost it.
Yes. What and maybe also, Blasea, if you want to unmute your mic, you could ask the question as well if you would prefer to.
I thank you for the opportunity. The question is more related to how you would adopt this algorithm for other processes, considering the interrelationship between the material, the process, and the design. Is there a plan to do so?
Yeah, absolutely. Good question. So this is my my last comment here about scalable physics-based simulation. So you know, when we talk about material properties, I mean, there are two interpretations of it. One is the anisotropic material properties that you get out of an additive manufacturing process. And so that's going to be orientation dependent. So in terms of this research, it's been focusing largely on the geometry of the printed parts. But you're right that when you start taking into account the physics and the you know, layer bonding, then there is going to be issues with respect to the overall material properties of the resulting shape. And so that is something that this analysis directly cannot do. So which is why we need to have physics-based simulation as a part of the loop. What we are doing is Xerox has come up with a metal jetting printer in the market last year. And we've built you know, physics simulations for that process, which is going to be a combination of, you know, essentially fluid flow and heat transfer, as it is with most metal additive manufacturing processes. And that kind of physics model that captures the layer bonding will then be used in conjunction with this geometric analysis to give you an approximation of at least the local material properties. And that needs to be homogenized in order to be able to get bulk properties. So the question is very valid, but this research as described here does not directly scale to including material properties. And there needs to be additional work that captures that.
Great. Thank you very much, Sai. Thank you for the good questions. And I believe it's time for us to move on to the second presentation. It's my pleasure to introduce Professor Carolyn Seepersad. Dr. Seepersad is a Mike Walker Professor in Mechanical Engineering at the University of Texas in Austin. She received her PhD in mechanical engineering from Georgia Tech in 2004, and she is the director of the Center for Additive Manufacturing and Design Innovation. And the topic of her presentation is the paper titled Stress Constraint Design of Functionally Graded Lattice Structure with Spline-Based Dimensionality Prediction. Thank you, Caroline. The floor is yours.
Thank you so much, Fiona, for that great introduction. And before I get started, I'd really like to acknowledge my co-authors. I know Zhenmi Zhang is also on the Zoom meeting today, and she and Connor Sharp really are responsible for not only implementing, but also really conceptualizing a lot of this work. And so it's been a real privilege to work with them. And I hope Zhenmi gets a chance to answer some questions when we go into Q&A. So we're really motivated with a lot of the work that we do in being able to additively manufacture complex structures and mesostructures. As many of you know, that's a challenge to design these. We have lots of geometric details on different scales, and there's a large number of parameters that's required to design across these scales, especially when you consider designing not only the unit cell, but also the lattice structure itself and surrounding structure. So often the way we handle this is to homogenize the behavior of these unit cells that we use in these lattice structures. And so typically then we create a homogenized stiffness tensor that you can see in blue here. And that homogenized stiffness tensor then we use to be able to predict the properties to analyze, for example, the overall compliance of a lattice structure. We can also use it to calculate a homogenized or volume average stress locally within the structure. It's convenient to do this. We can create these homogenized models offline by interrogating a single unit cell with, for example, a finite element analysis, and then building a surrogate model of those unit cells that we can use when analyzing the overall lattice structure to help reduce computational expense. But there are some challenges associated with this approach. So the first one is that when we use homogenized stress alone, we can't reliably predict failure within the mesostructure. Actually, that homogenized stress typically underpredicts peak values of stress in the overall lattice structure. And that's something we're very concerned about. So in this talk, in this paper, we present a worst case approach, a worst case stress computation that we can do that's much more computationally inexpensive than going back to the original homogenization model. We're also interested in being able to predict the properties of these lattice structures across a very wide range of densities. Most analytical models for lattice structures typically hover around sort of the 10 to 30% density. And to properly do topology optimization of these lattice structures, we'd like to range over a much wider range of densities, say from 2% all the way up to 100%. So we build surrogate models over a wider range of densities here. And then finally, to enable even greater computational tractability, we also create a B-spline representation of the lattice structure. So instead of having a large number of design variables, typically scaling with the number of unit cells you have in your lattice structure, we use a B-spline representation to reduce the dimensionality further, and also critically to smooth the lattice structure to make it easier to manufacture. So to first look at the worst case von Mises stress. So in this case, lambda, which is in blue on this slide, is the largest von Mises stress at any point y in a unit cell, given a homogenized stress. And so one of the things we can do here is we can derive that worst case stress lambda directly from our homogenization procedure. If we look at this term in purple, which is really a product of the homogenized stiffness tensor, deviatoric stress, and a mapping from macro strain to meso stress, if we calculate the largest eigenvalue of that tensor, then we arrive at this worst case stress multiplier lambda. And so that is helpful to us in predicting worst case stress and preventing the structure from exceeding that worst case stress. So for example, for homogenized stress or load of any direction or magnitude S in this case, when we multiply it by our worst case stress multiplier here, lambda, then we know then that that quantity will always be worst case. And so the von Mises stress will always be less than that quantity in that unit cell. And so from that, we can form a failure criterion, which you see here in the bottom, that multiplier lambda max, which is the maximum of lambda over the entire unit cell, all locations in the unit cell Y. Then we can create the failure criterion that you see below, and we can implement it. And so critically, that lambda is actually parameterizable as a function of the density. And so here you can see a surrogate model that we've created for a particular unit cell. This is the octet truss unit cell, where we predict lambda as a function of the density of that unit cell. And in black dots, you can see the data that was used to fit the model. And then the solid line there is the surrogate model fit to that. So we have surrogate models now that help us predict maximum stress, worst case stress, as well as that our constitutive tensor. We also use B-splines here to be able to represent a field, a density field across a structure with reduced dimensionality. And so essentially we use a B-spline here that we've borrowed from CAD, from computer-aided geometry. And we can use it to predict density at any particular point in the structure using a reduced number of design variables, which correspond to the control points that are used to modify that field. So here gives you a sense of how well that B-spline representation can do. This is just a standard cantilever beam optimization problem. On the right-hand side, you can see what a 20 by 32 finite element mesh, how it performs and what it looks like. Up at the top, you can see this is a SIMP penalization parameter of 3, which is designed to provide solid and void and clear distinctions between the two. And in the bottom row, you can see that penalty factor is now 1. It doesn't exist. And so this is more of a smooth representation, which is actually what we're seeking with the lattice structure. And in this case, you can see that with a 20 by 20 grid of control points for our B-spline, how well we do and how the compliance matches what we do with the full mesh. And then how well we can do with the 10 by 10 grid of control points, which is about a 6 times reduction in the number of design variables in this case. So it's a pretty promising approach. We implemented it using a combination of MATLAB and Abacus with user-defined subroutines for our constitutive models and our worst case stress calculation. So here's an example of a cantilever beam problem. You can see the load being applied over here on the right and the supports being applied on the left. We're minimizing compliance and restricting volume to be no more than 40%. And I'll show you some results with and without stress constraints. So here you can see what happens as we refine our control mesh. This is the underlying mesh for our B-spline. Here you can see this is the initial compliance, and this is how with a 6 by 6 mesh of points versus a 10 by 7 versus a 14.8, you can see the compliance values that we're achieving with our optimization. So once we reach a certain number of control points, we tend to do quite well with our optimization. Here you can see some results from that cantilever beam problem with a 25 megapascal load with no stress constraint and with a stress constraint. In this case, you can see that the maximum worst case stress is actually quite similar to our yield stress. So when we implement that stress constraint, we don't see a lot of difference in material distribution or our contour plots of stress and the resulting structure. But if we increase the load and double it to 50 megapascals, then we start to see quite large levels of stress. And in this case, by implementing our stress constraint, we can see those levels of stress, black being worst, start to lower. And we can also see small changes in material distribution within our structure. We can look at different unit cell types. So octet truss was used for the previous results. Here's a different type of unit cell that's stronger has higher normal stiffness, but lower shear stiffness. And you can see very, very different stress distributions coming about from our optimization procedure. You can see that this particular unit cell, unsurprisingly, has much higher stress levels because of the bending nature of this load. And so we can implement our stress constraints again to reduce the stress, change the material distributions. We have a sacrifice in compliance here. The compliance is not quite as good, but the stress is much better. So just in summary, some of the things that we've talked about is a significant reduction in dimensions using our B-spline parameterization. That could be even more significant in 3D. A tractable and accurate multi-scale design via surrogate models for stiffness and stress, where those stress models are surrogate models that are calculated as part of our homogenization routine and provide much more conservative estimates of the stress. Everything is generalizable and easily computable, like I said, via the worst case stress estimate. We can, because we have reduced dimensionality with our B-splines, we can work with commercial software without analytical design gradients, but we can also provide analytical gradients for our B-spline representation if we want to do that. And we've shown it with some other problems as well. We didn't have time to review all of them here today, but we've shown it with several different problems. We've also done some additional work that we don't have time to talk about today, but looking at process-aware design of lattice structures as well, taking into account direction dependence of material properties. And that's also published in a companion JMD paper that was published in 2021. And so with that, I think my time is about up. So I'll acknowledge all the folks who helped us with this work and sponsored this work. And I'd be more than happy to answer questions and invite JMD to help answer those questions as well.
Thank you very much, Caroline. It's very interesting research. And I would like to open the floor for questions. Is there any question? You could type in the chat, or you can just raise hand. We will cue you for you to ask questions directly. While we're waiting, well, oh yes, Wei has a question.
Yeah, so Carolyn, it's a very interesting work. I think it's also very useful. I wonder whether you have given any thoughts to accommodate, say, nonlinear material behavior, and how the constitutive relationship can still be passed throughout the multi-scale, and how do you manage the optimization complexity?
Sure. JMD, would you like to address that question?
Yeah, sure, I can take a stab. Yeah, so nonlinear, I think, I guess for nonlinear simulations, I guess it depends on the type of failure. So if we're looking at, so in this particular study, we were looking at, so we define failure as a point where, like, you know, the maximum Meisel stress inside the unit cell exceeds the yield stress, or whatever failure stress we would like to define for the material. So I think it would probably, so for nonlinear materials, first, I think we have to define, probably update the definition of what failure we're interested in simulating. But if, you know, I think if the criteria is to be extended to simulating, like, so for example, plastic flow, then I think it's important that the, like, you know, the anisotropic nature of the failure to be taken into account. So one of the advantage, and at the same time disadvantage of this approach, is that it's isotropic. So it assumes that the orientation of your macro stress tensor or your homogenized stress tensor doesn't actually play a role in dictating what this criteria is going to be. And I'm assuming if the interest is to simulate, like, you know, the plastic deformation in a nonlinear simulation, then I think that anisotropic behavior probably needs to be accounted for.
Thank you.
Great.
Can I ask a follow-up question? This is Alicia.
Sure.
So I'm just curious, this is rather basic, but I guess it does relate to the nonlinearity. When you apply the homogenization, obviously you apply the periodic boundary conditions. So I'm just curious how you actually calculate the stress inside the unit cell with that assumption. And following that, then obviously you will need the nonlinear homogenization to calculate those stresses in order to calculate the nonlinear stresses. I'm curious what your thoughts are on that.
Yeah. Okay. So sorry. I'm assuming I'm taking this question as well. So
Yes.
for the stress calculation from the homogenization calculation, what we do is that we would apply 6 unit macro stresses, and these are the average volume average stress that would be applied to the unit cell. Actually rather strain. And then for each one of these strains, we would get a stress distribution within the unit cell. Then by the principle of superposition, we can, like, you know, just add it up to be able to find the stress distribution for any arbitrary applied macro strains, and likewise the macro stress. So what I mean to say is that this homogenization calculation already gives you an explicit mapping from any macroscopic quantities into, like, you know, the actual specific distribution of micro stresses that are inside the unit cell. So that, I hope that answers your first question. And for the second question, yeah, so nonlinear simulation, we were very much interested in looking into it, but we didn't get a chance to investigate. But I assume that it, yeah, I think you're right that the process will be a little bit more complicated.
Great, thank you. And Julián, you have a question.
Yes, so, you know, first of all, I think this is very, very interesting work. And I think this idea of using the maximum stress, it's pretty elegant and clever. One question that I had was, do you have a sense of how conservative it is? So once you choose the octet truss, right, like, did you have a chance to, for example, do an analysis for a structure with just a few cells to see how far you may be, you know, for some of the examples that you showed, so for example, for a cantilever beam or what have you?
JMD, I don't think we did that comparison, did we? You can
no, yeah,
take that
no, we didn't.
well.
Yeah, but I think so. I mean, I guess conceptually, I guess how conservative it is depends on how anisotropic the real failure surface for the unit cell is. So I feel like if it's, you know, especially elongated, you know, I guess, for example, what I mean is the material is particularly weak in a particular load direction. Then you know, it could be very strong in one direction but very weak in another direction, then it's the weakest load, I guess, direction that would be used to choose the stress nullification factor. So it could be quite conservative. Yeah, but but I guess the plus side is it's quite easy to use. You have a single number to deal with rather than all of this isotropic nature. Yeah.
Yeah, that's right. I think Jenmi's point is a good one, that if your unit cell is quite isotropic, then this should represent the maximum stress quite well, regardless of direction. But if your unit cell is quite anisotropic, then it could be extremely conservative, depending on whether the stresses are aligned, right, with how the stresses are aligned with the orientation of the unit cell. So it really depends a lot on that.
Great.
Great. Thank you. Thank you very much for this very interesting presentation, and we can now move on to our next presentation. It is my pleasure to introduce Professor Kade Whitefoot. She's an associate professor in mechanical engineering and public policy at Carnegie Mellon University. She obtained her PhD in design science, which includes mechanical engineering and economics, from the University of Michigan in 2011. And today she will present her work and with her co-authors on part consolidation. So Kate, you can take it away.
All right, thank you so much. Hi, everyone. It's great to be here to see you guys. And I want to thank Fiona and Julián for organizing this and bringing us all together. I'd like to acknowledge my co-authors on this paper, Jiango Ni, who's now an assistant professor at Tsinghua University, Sang-Jin Jung, who's now an assistant professor at Southern Illinois University, and Barak Kara, who's also at Carnegie Mellon. And so this paper was motivated by the potential advantages that we can have in using AM to leverage parts consolidation across a large range of systems. And of course, one advantage of using AM for parts consolidation is that it can improve performance, eliminate assembly steps, and potentially significantly reduce costs from taking out those production steps from assembly. But in other contexts, we've also seen that consolidation has the potential to increase other production inputs, such as the material and the labor that's needed to produce these parts. So that can offset the potential production cost advantages that we might be able to see from parts consolidation. And prior work had examined methods to select parts for consolidation using AM and to maximize the amount of consolidation that was feasible to maintain part performance, but it hadn't looked at trade-offs of consolidation with other enterprise objectives, such as production time and costs. And so we developed a method here to optimize parts consolidation to minimize production costs or time, as is important for the user in their context. So just an overview of the method. We start with a generation of selecting possible consolidation candidates of different interfaces within the system to consolidate. We then filter them for feasibility as well as for structural redundancy. And from there, we determine the optimal configuration within the build envelope, both in terms of the part orientation as well as the layout of parts into multiple batches within the build envelope. We then select the optimal processing parameters, including travel speed, use that to evaluate the total production costs and time from setup of the AM build to including all post-processing steps. And then we optimize that consolidation for either minimizing production costs or minimizing production time. And so for a short presentation, I'm going to focus in on how we created the method of generating the candidates for consolidation and evaluated them for reducing production costs and time, and some insights that we came out on this. There's further details in the paper, and particularly I just wanted to call out that this filtering process for structural redundancy was a contribution in the paper that is actually really important for reducing computational costs of the optimization process. So this work was done in collaboration with an industrial partner, and the test bed system that we selected for this work is an aft fairing. So you can see the part here, and we considered both titanium and aluminum materials for this system. So how we generated the candidates for consolidation is by representing any given input system. So here we've got our fairing subsystem, representing that with a network graph where the nodes are the components of the system, and then the connections are interfaces. And after filtering for structural redundancy and feasibility, we can convert this network structure into genetic algorithm coding, where we're representing whether or not those interfaces are consolidated as a 1, and if it's not consolidated, then it's left as a 0. So in terms of evaluating the total production costs and time associated with these consolidation candidates, we use a process-based cost model, where the data for this model is sourced from a variety of companies that use AM across multiple industries. And so we use data from 14 companies for the electron beam melting process with titanium produced in the United States. And then we supplemented this data as well with production data for aluminum and wire-fed DED to compare different modalities and material uses here. So these are the results of using a powder bed for the optimization of our fairing made out of titanium. And in this case, the optimum is to reduce the number of parts from 10 total to 4. I'll talk more about that, but it's an important insight from our method that the optimum was not to consolidate the entire system. And the outputs of this method are also include the optimal build orientation and collection of the parts into separate batches, as you can see right here. So the total production costs associated with this fairing reduced 20% after optimizing the consolidation of these parts. So here I'm plotting in red, this is the Pareto frontier of the production time, as well as the frontier for the production costs at different levels of consolidation, where the degree of consolidation is defined as the percentage of interfaces that were consolidated. And so here you can see the key trade-off that we discover is that as the degree of consolidation increases, we see a reduction in the costs associated with machine setup, as well as assembly steps and taking those out of the production process. But that is countered by increasing costs from the support structures that are needed for these larger consolidated parts. And so that results in an interior optimum of consolidation. And you can get an intuition that this would apply to other systems as well, because as you increase the number of parts that are consolidated, it's more difficult to orient it within the build to reduce the support structures that are needed there. So we ran this over a number of different subsystems with different geometries, materials, and AM modalities. And this figure is qualitatively summarizing the results that we found, which are that for parts that have what we call a smaller shadow volume, which is proportional to the amount of support structures that would be needed for that part. For modalities where we have a lower machine cost or faster deposition, and for parts where the assembly operations are more expensive, the optimal level of consolidation can be at full consolidation. But for other systems, we tend to see interior optimum where we're not consolidating the entire system. So just some examples here, looking at a toy plane and comparing that to a chair and using different modalities. Here we've got powder bed fusion and powder fed DED, as well as comparing across titanium and aluminum. We can see that for the toy plane, this has a larger shadow volume compared to the chair because of the extended wings. And so in this case, when we produce this product out of titanium, we get an interior optimum for the degree of consolidation. But if we switch to aluminum, which is of course a cheaper material, then the optimum shifts towards full consolidation. And for the chair, because the shadow volume is lower, we can see that even if producing it out of titanium, the optimal level of consolidation can still be 100%. We also find an interesting effect associated with the scale of the part. So as a product is scaled up in size, the shadow volume and the support structures that are needed rise approximately proportionally to the cube of the scale dimension, whereas the assembly costs that are required rise approximately with the square of the scale factor. And so as a result, we see that for all else equal, larger scaled parts, the optimum degree of consolidation is much lower. And in fact, for some systems, it doesn't make sense to consolidate any of the parts. Whereas if the part is scaled down, then the optimal degree of consolidation moves towards full consolidation. So in summary, we find that the key trade-off of what level of consolidation is optimal is between reducing the assembly steps with increasing support structures that are required for these larger consolidated parts within the build envelope. And we find that smaller shadow volume, lower material or machine costs, and faster deposition rates are the key drivers to move optimum for certain parts and certain AM modalities to 100%. But for other parts, we tend to see an interior optimum. And there's also this important part size effect. So because the support structures increase faster with size than with assembly costs, we tend to see that smaller parts are likely to have their minimum production cost and time in terms of fully consolidating that system, whereas for larger parts, we recommend to industry to anticipate not having full consolidation in order to offset these higher support structure costs and time. Okay, and with that, I am happy to take any questions.
Thank you very much. So we now open the floor for questions. Just a reminder, if you want to ask a question to our speaker, please either type it in the chat and we'll relay to her, or raise your hand, and when we give you the turn, you can unmute your mic and ask the question.
Well, I have a question for Kade. Thank you very much, Kade, for the presentation. So it seems like in the filtering stage, you're looking at one of the criteria is a structural redundancy. I'm wondering, how did you decide the structural redundancy, and in what manner you're making the filtering decision?
Yeah, great question. So we used what we call a closed loop filter. And so the basic criteria there is that if the number of interfaces that are consolidated, you can subtract one of those interfaces, and effectively the part would still have to be produced as one piece within the build envelope and would maintain structural rigidity. Then we filter that out of consideration. We basically consider that as equivalent to consolidating that last interface in that subsystem. And that can be really important because for these large systems where you have many different types of interfaces, we don't want the genetic algorithm to consider all of these parts where functionally when we're building the parts, it's not really a separate design. We wouldn't get the advantages of leaving that extra interface not consolidated.
Thank you.
We have a question in the chat from Alicia Kim, and the question is, she's wondering how you incorporate the costs of different fastening or joints into the overall thickness of how many parts you have.
Yeah, that's a great question. So, yeah, we built the method so that the users can input a specific assembly cost. So it really can be whatever the assembly operation is in your production facility. But the two that we investigated with our results were riveting and welding, because they were most relevant for the parts that we looked at. And so in those cases, the key there is really the time that it takes to conduct the assembly operations, and then costs associated with labor and inputs. For our systems, we see that riveting is a more expensive assembly operation than welding in this particular case. And so with more expensive assembly operations, that gives you an incentive to consolidate further parts together, because that is a larger driver relative to the support structures.
Great. Thank you very much, Kate. And thank you for the questions from the audience. And now I think we should move on to our last presentation. And it's my pleasure to introduce Professor Nicholas Meisel, who is an assistant professor at Penn State University. And he is the associate director of the engineering design graduate programs there. And he has received his PhD from Virginia Tech in 2012. And the presentation is based on the publication titled as "But Will It Build? Assessing Student Engineering Designers Use of Design for Additive Manufacturing Considerations in Design Outcomes." Nick, the floor is yours.
Great, thanks so much, Fiona. I really appreciate it. And thank you again for the invitation to speak today. So as was mentioned today, I'm going to be talking about some research out of my group, the Made by Design Lab at Penn State. So as was mentioned, I'm an assistant professor of engineering design there. There we go. So this work was previously published in the September 2020 issue of Journal of Mechanical Design. As was mentioned, it's But Will It Build? And this was actually done not just by myself, right? So this was a very large team for a multi-year project. This involved my former student, Rohan Prabhu, who's now an assistant professor at Lafayette College, Dr. Tim Simpson, Dr. Stephanie Cutler, and Dr. Scarlett Miller. So this really took everybody to sort of make it a success. So the scope of this project is a little bit different from some of the projects that we've heard about to this point. So whereas a lot of the discussions so far have been around the idea of optimization and automating design, our study was much more about the idea of what happens on the human side of design for additive manufacturing. So thinking sort of to that quintessential napkin sketch that engineering designers tend to start from. So that was sort of the approach that we were taking here. And the idea is around the fact that for additive manufacturing, it's not just about can we account for the limits of the process, right? So things like material deformation through warping, surface finish, accuracy, support material removal, but also can we leverage additive's capabilities, things like part consolidation, which we just heard about, topology optimization, lattice structure, mesostructural design. So when you think about sort of the human side of design for additive manufacturing, to really have a robust product, you have to consider both sides of this coin. So what we've termed what has been termed opportunistic design for additive and restrictive design for additive manufacturing. The challenge we run into is that educational interventions to try to teach students and teach designers how to leverage this vary in their focus on the different sides of design for additive manufacturing. So I have an example here pulled from hubs.com, focuses almost exclusively on this idea of restrictive design for additive manufacturing. So while this encourages students and designers to figure out, can I make something? It doesn't necessarily help them understand, should I make something? And the problem here is that if we don't address both sides of this when we're educating designers for additive manufacturing, it's possible that they're going to unevenly consider the different aspects of design for additive manufacturing, especially in early stage design when they're not turning to all the optimization tools, right? It's just what sort of concepts can I come up with off the top of my head? So the questions we wanted to look at really were, to what extent do engineering design students incorporate opportunistic and restrictive DFAM into design tasks? And then also, how does this focus vary depending on the educational interventions that we give them? So to answer this, we had 3 specific research questions. The first related to just how does the use of design for additive manufacturing, both the opportunistic and the restrictive side, help students achieve the objectives of a particular design task. For our case, we were looking at minimizing build material as well as build time. The next one was looking at how does a particular educational intervention affect students' achievement of these objectives, as well as their integration of different design for additive manufacturing concepts into their designs. And then lastly, we wanted to see how do these design for additive concepts manifest in the designs, right? So if they're taking advantage of, say, shape complexity, what does that look like in the designs that they're coming up with and that they're hoping to print? So for our experimentation, we had students participate in either a restrictive design for additive manufacturing focused or what we call a dual design for additive focused educational intervention. So dual DFAM is including both the restrictive and that opportunistic side. So this was a relatively short 20-minute lecture on each piece of design for additive manufacturing. So we started off by giving a pre-survey to the students where we would gather their previous experience, their self-efficacy with design for additive manufacturing, which would then lead into the educational intervention. So half of the students received just the restrictive design for additive intervention, and then the other half received both restrictive and opportunistic. Afterwards, the students performed individual idea generation. So we told them, kind of go wild with your ideas, and then they would evaluate those individually and come up with one final concept that they like. Then they would move to the group phase where they would come up with sort of a selected idea from the group, come up with a CAD model, and finally prepare for print. And then they would end with a post-survey, again, trying to measure their self-efficacy. So the task that we used for this is actually based on some previous work that we've done looking into task complexity as it promotes the use of design for additive manufacturing. So you can see the task here. Essentially, it's asking the students to design some sort of tower that can support this downscaled wind turbine at the top of it. So the tower has to be at least 18 inches tall. The reason why 18 inches is because it prevents them from being able to get the entire length of a tower along any one dimension of the printer that they were using. So they were going to have to use some sort of assembly here. And then we provided them with a series of constraints in order to really push that use of design for additive. So once the teams had come together, they had selected their final design, the teams submitted prepared build trays, so that way we could evaluate how well they met the task objectives of minimizing weight and minimizing build time. So in this case, they were just using MakerBot Print, which outputs the approximate material usage as well as the approximate print time associated with that. So to assess the actual designs that they came up with in terms of how they used design for additive manufacturing, we developed a new set of design for additive metrics that are sort of tailored towards this wind turbine design problem. So this allows us to score things like the part complexity, the assembly complexity of the geometry, the number of separate parts, sort of on the opportunistic side, but then even on the restrictive side, things like what are the smallest feature sizes that they use, what are the tolerances, how much support material is used in mass. So this lets us sort of quantify how well they're using opportunistic and restrictive DFAM. And you can see an example here of one particular tower and how this would score, for example, part complexity, relatively low since it's more or less just a prismatic rectangle used for a tower. And what we found in response to our first research question is that we can sort of see a connection between the use of certain DFAM concepts and how well those predict the students' achievement of the build material and build time objectives. So this is sort of combining all of the students, both from the opportunist, the dual group as well as the restrictive group. So as an example here, we saw a statistically significant connection between the number of parts and the build time. So we have one here that is 12 parts, which ended up being over 1,000 minutes to print. And then we have one that's 3 parts and was significantly lower at about 920 minutes to print. Similarly, we saw a connection between the largest contact area on the build platform and the relationship between that to build material. So again, a lower contact area turned into a lesser build material typically. So what's interesting though is as we started to really dive into the solutions that the students were coming up with, we were seeing a very different approach that each one took to actually incorporating these design for additive manufacturing considerations. So these are a couple of example designs that we saw. So on the left there, you can see some examples from the restrictive group. All the towers fit together very nicely, but they're relatively plain. It's mostly just rectangles extruded 18 inches up. On the other side, for the dual group, you can see that they're starting to leverage a little bit more of the design freedom associated with additive manufacturing. But in these cases, they weren't able to be assembled because the tolerances were improper, right? And that tolerance is more of a restrictive concept. So when we look at this statistically, we ended up finding that there was a significant difference in how the different groups leveraged design for additive manufacturing. So for example, the restrictive group gave much more generous tolerances to the designs, since that was something specifically covered by restrictive DFAM. So they had a lot more success with the assembly. Same thing with support material. We saw that the restrictive group did a much better job of handling support material. The only aspect where the dual group did better was on the idea of the largest build plate contact. Because a lot of them tended to remove chunks of material, it resulted in lesser contact with the build platform. So we went another step further and we did feature analysis on 4 different aspects of design for additive. So how they removed material, how they accommodated for support material, how they connected different sections, and how they tried to minimize contact with the build platform. And what we found is that there were, again, significant differences in how each group implemented these different design for additive manufacturing strategies. So for example, for the part complexity side, we saw a lot more instances of just solid geometry for the restrictive group, whereas we started to see more bulk primitive cuts being implemented for the dual group. There were no significant differences on assembly complexity that we observed. But if we go to things like support material accommodation, here we see that for the dual group, we had a lot more challenges with inaccessible support material being included in their designs, as opposed to the restrictive DFAM group, where it was mostly easily accessible support. For the warping accommodation, we do see significant improvement from the dual group, partially because the warping accommodation is tightly coupled with this idea of part complexity. So typically, the more material you're going to remove to make a more complex part, the lower your contact area is going to be for the build platform. So these findings sort of illuminate the unique consideration of how do we get students to leverage design for additive manufacturing, and how does it sort of manifest in the designs that they come up with. So as I mentioned, this is just one part of a multi-year study that we've done. So these are 4 other papers touching on different aspects of this project that have also been published in JMD over the past couple of years. I want to acknowledge our funding organization from National Science Foundation. And with that, I think I'm just about at time, so I'll go ahead and stop here and answer any questions.
Thank you, Nick. Thank you very much for the presentation. So for the audience, please feel free to type your question or raise your hand. And I'll start with the questions. So these students that you mentioned, do they have previous design experience, or they are novice designers who's never designed anything before?
Sure, that's a great question. So it was actually done with a junior level mechanical design class. So they knew the basic principles of both additive manufacturing as well as the design process. But for the most part, they weren't really experts in design for additive manufacturing.
And you also mentioned there are 4 criteria you use to evaluate. I'm curious of design complexity and assembly complexity. How did you measure these 2?
So for our metrics here, it was done mostly subjectively, so sort of pulling from some existing metric work that's already been published out there. So for the most part, we were looking at just scored 1 to 3. Is it a relatively straightforward primitive geometry, or do they have complex curves that could not be machined, for example? Similar for assembly complexity, are they simple prismatic joints, or do they incorporate a little bit more complexity, like having locking features to them?
Okay, this is very, very interesting. And one of my research curiosity in design for additive manufacturing is always how can we look into multifunctionality, right? Mm-hmm. I'm wondering if you do actually look in function analysis and decomposition stage in your design curriculum. I know Penn State has a very big research on this, so I'm wondering if you touch that aspect.
So we weren't really focusing on too much on, we do talk about multifunctionality when we talk about design for additive manufacturing, but for this sort of challenge with the type of printer that they're working with and sort of the scope of it, it typically doesn't come into play too frequently.
Right, and we also have one question from the chat from Magdi Wahab. So the question is, was it based on 1 year of the student, or one class of student, or many of them?
Sure. So this particular study was based off of 1 year worth of students. So it's about 150 students each semester. So we used the spring and the fall semesters for this. All of the other studies that we've conducted through here, though, we're using the same sort of group conducted over multiple years. But for this one, it was just grabbing data from 1 year.
Great. Let me double check if there is any raised hand. You raised a hand and I didn't call you. Please just unmute yourself and ask question.
I don't believe there is one.
Okay, great. I think we are sort of on time for our presentation portion. And I think we are good to move on to panel.
Excellent. Let me switch to the gallery view here so I can see everyone. We are now going to open the floor for questions to our 4 presenters with regards to either their presentations, additional questions about their work, or general questions. So just a reminder that you can type your question in the chat or raise your hand. And I would like to get the discussion started with a question for all of you, and anyone can answer for the presenters. In your work, what did you find to be the most challenging aspect of incorporating specifically design for manufacturing aspects in the design?
Yeah, feel free. Whoever wants to start, answer this question.
Well, I can start, I guess. So I think, particularly when you're designing lattice structures, one of the biggest challenges that we've been trying to work on in our group a bit is that what we fabricate when we measure the properties, they really don't match the FEA predictions very well. And so, there's a number of different ways you can try to address that by, CT scanning the results and interrogating the results and things like that. So we've developed some techniques for trying to understand sort of the size and direction dependent properties of the struts that make up the lattices and bringing that information into the predictive models. And that helps a lot. But even if you do that, you do see differences from machine to machine and process to process. So taking an approach like that to be able to get your predictive models to better match what you build means that you have to have a well-characterized machine. And you also have to control the machine well so that when you do characterize it, subsequent builds are similar to that. So I think that's a big challenge, right? I mean, a lot of companies right now are working hard towards being able to qualify parts. And qualifying a bulk part is hard enough. Qualifying a lattice structure, something with so many multi-scale details is even harder. So I think that's a big challenge, right? Is qualification not just of a sort of a large replacement part, but also qualification of something that really takes advantage. It kind of links into what Nick was talking about as well. These opportunistic designs really often introduce more complexity into the structure as well on multiple scales. That makes it even harder, I think, in many cases to predict exactly what type of performance you're going to get and to be able to qualify those parts.
Thank you very much, Caroline.
So I can offer up some insight from ours. So, as I mentioned, we were focusing very much on sort of the conceptual phase, but what we find is that there is a lot of challenge translating good design for additive in a concept sketch to an actual CAD model, for example, for our students. So they might come up with something that really leverages the free complexity, right? The lattice structures, the freeform geometries. But then the minute you say, all right, now go make this in CAD, they find that bottleneck where it's very difficult to try to make that a reality just because of the natural limitations of CAD modeling and how they are mostly there to represent very traditionally manufactured geometries.
I absolutely agree. Kate?
Yeah, for our work, I mean, one of the tricks with AM is there's so many design decisions and process decisions are so strongly coupled together, right? So when we think about using sort of automated design tools and moving towards more fully automated optimal design tools, those very highly interrelated parameters are very tricky for us to get a handle on. And so, certainly like when we change the geometry when it comes to AM, that not only impacts the structural performance of the part, but it impacts how you lay out the parts within the build envelope, and it affects the nearby parts and their own geometry and how you design those parts. And so what we are trying to do in our work and sort of follow-up work, as well as you saw a flavor of in this paper, is get a handle on what proxy parameters can be used to get us like 90%, 95% of the way there without having to entirely embed all of these internal optimization loops within design optimization for AM.
It's very interesting, proxy parameters. This is the first time I hear this terminology. And it's very representative of the situation we're dealing with. Often in the end, we will just say, okay, we reached to about 90% of the conform 90% of the simulation result. There you go. It's good enough. I think that's definitely directly related to the complexity. And I'm wondering how Sai thinks about this, because your work has so much computational aspect.
Yeah, I mean, so there's two parts to the answer. So first of all, from an industry perspective, right, like I talk to a lot of people in the aerospace and defense industries, right, like, and people who are using design tools. I'm sure many of you do too. And one of the things that we hear consistently is the inability to incorporate the design optimization techniques that are out there in research into their workflows, partially because of the disconnect between CAD systems and, where our design optimization tools are, but also partially because we simply don't have the fundamental computations really figured out in order to be able to take the multi-scale effects that I was talking about earlier. So suppose you're dealing with complex melt pool geometry and how that affects the porosity and how that in turn affects the resulting material properties, and how can you process that with a combination of additive and subtractive manufacturing. It becomes a really composed challenge problem, right? Like for manufacturing incorporated into early stage design. So I think there's at least two things that need to happen. One is the incorporation of post-processing constraints into the formulation of the design for additive manufacturing problem, whether it is machining, whether it is powder removability, whatever it might be, right? Because we don't necessarily always take that into account. There's always that iterative process that happens after design optimization and manufacturing planning that leads to the same problems we had traditionally with design and manufacturing. So that's one of the one of the things that we've done is to identify how manufacturing constraints can be represented as a continuous field to be able to augment it with the Lagrangian formulations, for example, in topology optimization, right? Like there's ways of doing that, but that's just one of the ways. And if you're looking at processing with composites, for example, or with high-axis NC machining, there's still a bunch of open questions. So the two-part answer is that not only the tools don't exist out there for this kind of composed consideration of manufacturing and early stage design, but there is an adoption problem in industry as well, because there's simply just no way of going in from the unparameterized shapes we deal with in topology optimization typically to the more parametric view of computer-aided design. Julián's work is an exception, I think, over there.
Maybe Julián would like to add a few things.
Yeah, I think particularly, I guess, in my experience, I think perhaps one of the most important challenges in trying to accommodate all of these manufacturing considerations, particularly in topology optimization, which is what I do, is that we don't have the language to do that easily. And by that, I mean that the geometric representations that we use of the structure do not allow to easily capture and embed those manufacturing-driven geometric considerations into the topology optimization, right? And certainly, the density-based and level-set representations in topology optimizations have been extremely powerful and useful over the years to do a lot of things, but they just make it very difficult to be able to incorporate a lot of these geometric-driven considerations into the design. And if to that, like Sai was saying, if to that you add the process considerations, right? For instance, a process-induced effect, then that complicates things even more, right? And this is not only in additive manufacturing. Even if you're doing a casting, right? Your topology optimization can produce something that you can cast and is structurally good and everything, but you don't know if it's going to end up with a lot of pores or hot pairs and things like that. And so we're at a stage in which I think we're still relatively far from being able to produce designs that already conform well to the manufacturing process, not only geometrically, but also physically.
Great. Well, thank you for all these comments. And I think we have about 5-6 minutes left. I'd like to talk a little bit more about the geometric modeling aspect, because for now, that's one of my main interest in design for AM is driven by what you have mentioned before, that the challenge of having a geometric modeling tool that is able to represent those geometries, such as lattice is one of them, complex freeform structures, for example, used by students. Nick, I'm wondering, when students are in your project, when they're trying to do modeling, what kind of software are they using, and was there any particular shape they want to generate, yet was not able to model using we use SolidWorks, right? It's very basic, forget about very complex geometries. And for Carolyn's function graded lattice structure, what kind of modeling tool did you use? What kind of challenges? I've seen unit topology in your presentation. I'm wondering, when you try to vary the thickness or density of the structure, was there a very smooth process or challenging process? I'd like to get your comments on the geometric modeling perspective of design for AM.
So for the projects that I was talking about, we were focusing mostly on things like SolidWorks. Some of the students prefer using Autodesk Fusion 360 is becoming more popular with them. So very sort of standard CAD packages, I would say. We are seeing some of the students who are really diving into the geometric modeling with design for additive, at Penn State at least, starting to shift towards other software like that can handle implicit modeling, so something like N-topology. We're also starting to see a bit of an interest in things like voxel-based modeling for multi-material structures. But still, the overwhelming majority of it is, at the student side at least, is done using just straightforward SolidWorks, Inventor, things like that.
Thank you.
So for us, I don't really think this speaks too much to like commercial CAD software, but in terms of representations, I can speak to that a little bit. So one of the things I didn't talk about is when we design our lattice structures, we use the geometric projection method, which Julián has done an immense amount of work on. So we really build on a lot of the things that Julián has done in that area. And so that allows us to explicitly account for the size of the struts in our lattice structures. And so then we can also think about like size dependent properties and things like that and what we can and can't build. And then in terms of like lattice structure overall, one of the reasons for using the B-spline representation was to smooth the transition of the lattices, because it is very difficult to have harsh transitions in lattices. It's hard to build those lattices. And sometimes you can get into situations where, you know, in a structure, you do want solid and void, but in a lattice structure, you may no longer be able to build. That may create a cavity, for example, in a metals machine that it can't build around. And so that's one of the reasons we were using these B-spline functions to kind of smooth the lattice structure from place to place. It also makes your homogenization models a little bit more accurate than if you weren't smoothing it. So yeah, so those are some of the things that we've done that relate back to, I think, to representation.
Yeah, great, thanks. Sai, you have many experience with the voxel-based modeling.
Yeah, I mean, I want to add to what Carolyn was saying, which is that, you know, I think a lot of the design for additive manufacturing techniques, they either use parametric shapes or they use unparametrized shapes. When you're dealing with topology optimization, you often let the computer come up with the final shape, right? Like, so you don't really parametrize it in any specific way other than constraining the feasible design space, you know. And however, if you look at software like Entopology, for example, they're all about, you know, lattice-like structures that you can parameterize in an implicit way. So I think we should look a little bit into the future, and I think the CAD systems need to evolve in such a way that they support a hybrid combination of being able to represent unparameterized shapes as well as parametric lattice-like properties. Now, part of that could be in the choice of the representation itself with voxels, for example, and there are a lot of work that's been done with so-called hierarchical spatial indexing, so hierarchical voxel representations that can give you a very fine level of detail in your geometry while also you know, reducing your memory footprint. But the downside of that is that you don't have parametric representation of the voxels, right? Like, so there's design intent that is a little bit missing there. Right. So the hybrid system has to be able to capture both of those things, which means boundary representations are never going to really go away. But then voxels are emerging as a sort of really nice alternative, right? Like to think about three-dimensional modeling, especially if you have varying material properties or material distributions inside your shape.
Exactly.
So what Carolyn was talking about in terms of B-splines as a basis function to be able to represent geometry could also be extended to material properties, and she covered that too. And B-splines are one of the basis functions. Some of the work we've done in the past was about using Laplacian eigenfunctions. So there are many basis functions that we can use depending on the kind of problem that we're working with. So I think that we have to have a push from the community to direct the research towards like thinking about really what the future of the representations for design software for additive manufacturing needs to be because of all these issues. But that's just my perspective.
Well, I agree. Thank you very much. And Gary raised hand. Gary?
Yeah, hello, hi. This question for Carolyn. And you mentioned using implicit geometry. And from what I read, it seems it's all parametric. They have full control. And sounds like using very few lattice structures. Find about that. So it seems like it's not, you're still dealing with a lot of variables, is that right?
I think I missed the. Oh yeah. Yeah. Okay. Sorry about that. I think I missed the first part of your question, Gary. But it sounded like you were asking about how many variables we still have left, even after we reduce the dimensionality of the problem.
I'm just asking about implicit geometry modeling. Of course, no one mentioned is Entopology, right? They said they use implicit geometry with a few parameters can control the lattice structure definition. So what do you find about that?
So I think Yeah, I mean, I think the you know, going back to Sai's point about using some of these implicit modeling approaches, right? Basically, you know, I would classify them as sort of field functions, right? Where instead of controlling something at a very high fidelity level, you're finding a lower fidelity representation that gives you the ability to manipulate it with enough fidelity, right? To match what you can make or what you might be interested in. Just because you can change material from voxel to voxel, no, it doesn't necessarily mean that you should, or that that's a good thing, or that it gives you lots of advantages. I mean, I think there's a ton of upside to using those types of implicit modeling approaches, right? I mean, entomologies kind of showed that in that, you know, it's incredibly flexible to be able to, you know, tile an arbitrary geometry with lattice structures. I think from the design and from the design optimization standpoint, that was one of the perspectives we took in our paper, is that if we can reduce the dimensionality, we can get almost all the performance we need, but with a lot less computational expense, right? A lot less computational complexity, partly because we have fewer variables, right? So we can search the space more quickly, especially for problems where, you know, maybe analytical gradients aren't available. And then it becomes more difficult to search the space and more expensive to search the space, sort of a generalizable approach. So I'm not sure if I answered your question, Gary, but those are the first thoughts that came to mind based on what you mentioned.
Okay, thank you.
And for Kade, I mean, when we do part consolidation, I think we do face, well, the challenge we face is less of a geometric modeling, but more towards, let's say, function perspective, right? Filtering through, if we can do the filtering correctly to select the candidates for part consolidation.
That's right. And it's, you know, I talked about sort of functional redundancy in terms of the AM build itself, but more than that, there's a lot of considerations that go into, if we make more consolidated parts, then it has the issue of affecting yields within the production process, right? And so it really does, I think the research community is now at the state of not necessarily moving towards full consolidation in all conditions, right? We have to look at what are these trade-offs, because when you lose, you know, it depends how defects are sort of distributed across the system, and if you lose it because of a defect during the production process, you lose the whole part when it's consolidated, and that can be really important for when we're thinking about minimizing production costs.
Yeah. Last call for additional, thank you. Last call for additional questions before we move to our social networking stage.
Yeah, I have one additional comment for the part consolidation work, Kade, and is that in addition to the things that you consider, I guess there is also an element of the structural integrity of the joints, right? Because having joints in general is not good. They have less strength than the individual members, right? Where you're using, you know, whatever, adhesives or mechanical fasteners. And so there would be probably an additional criteria, you know, among all the ones that you consider, where, you know, it may be ideal for several reasons, where it's a strength or maybe it's a leak, you know, a potential leak, in which you actually want to have less joints.
Oh, interesting. Yes, to get functionality out. Yeah, that's a really interesting concept. And it's another example where it would couple with the geometry that you want from your parts as well, because as you change the joints throughout the part, your geometry potentially could shift in other directions once we account for that.
Definitely, and I consider that to be a possible connection to subsequent topology optimization, since most of topology optimization works with single component, and once we decide what parts can be consolidated, you would have opportunity to see if now it's a single component, right? You can optimize it. That would be interesting research to look into. Okay, so thank you everybody. Thank you to the speakers to give us very interesting presentation, and thank you for all the good questions. Now please use the link that is in the chat, the Gather Town. Click on that. You can continue with your Zoom link while trying to log into Gather Town. And once you are in the Gather Town, meeting rooms, then you can quit the Zoom. Actually, that's my recommendation. And Jenna and Amy and I will also, and maybe Julián as well, will remain in the Zoom. If you have any questions to get into the Gather Town, please let us know. So hopefully I will see you there in a few minutes, the virtual meeting place. Exciting.
And for those of you who cannot join us in Gather Town, thank you very much for making time today to join us. And we look forward to seeing you at some other time, hopefully in person.